Today, I'll turn it over to Marc Millis, who is going to give a summary of what this morning is going to be about, and is also giving the first talk. So, Marc, it's all yours.
Okay, thank you. Okay. The main things I'm going to be talking about today are the grant and a little bit about Tau Zero and then some of the other things. And I've got a lot to cover, so there's some slides that I might just kind of skip over, but I understand these things will be recorded or that are available online. And also, here's my email here if you want to follow up on things. One thing I've been noticing is that the various interstellar things that we're talking about kind of can be grouped into three categories or acts. The early precursors and forays, which I define as being launched from Earth without any extra infrastructure in space. And then a lot of the large concepts that require infrastructure in space to be built to construct the vehicles, to find the propellants and whatsoever. And then the undiscovered future of breakthroughs that might happen, and there's always unexpected things that have happened in history. And the reason why I make this demarcation is because it's very difficult to compare one of those eras to the others, but it's easier to compare options within those. Also, just the way I look at things and the way I would love to see the future pan out is that a variety of complementary activities going on rather than just one thing that is going on. I would love to see NASA to continue to launch deep space probes, interstellar precursor missions, ideally one each decade that's even more advanced than the other. I would love to see the progress on Starshot continue and see what they will be able to deliver. I also like to see the infrastructure in space, the kind of things that not only for the Moon and the Mars things, but eventually that these interstellar ideas rely on to be continued to be built. And for all those other things that are far from the point now of starting any mission things, there's the basic research to figure out how to do them, that research will happen and cover the spectrum of things that need to be covered. And the last one to comment, which will come up again, is the energy levels we're talking about are enormous. And I hope that we also mature as a society to be able to handle those kind of energy levels responsibly. The other thing is with these meetings, and one of the things I like about Tau Zero, this is an opportunity for feedback. I want you to critique this talk, not only for the sake of the talk, but the grant that I put together, I'm supposed to get community feedback on what you think about what we're doing. Some rules though. If you send me feedback, please do it in writing. I have a terrible memory for things. If you say something, I will forget it 15 minutes later. If you specify some value from a reference, please tell me the reference, because I've had people send me something but not tell me where they got it from, and I can't use that. Or just send me the reference without telling me what was it in that reference that I really needed to know. So if you do contact me, please follow these things. Okay. This is getting to the grant. To solve a problem, you first have to understand the problem. And interstellar flight is not the way it's not like other space endeavors. The timescales are beyond predictability. The energy is comparable to nuclear weapons, multiple nuclear weapons, the higher and higher missions you go to. And we can't just do this by extrapolating, can't do everything that we've envisioned by extrapolating the technology we need to have. So this is an opportunity for revolutionary things. So the traditional methods we've used for mission trade studies does not really fit this category. The goal of the grant is to help create a process to compare these various options to arrive at what research should we fund tomorrow that will have the most leverage? Is there some item that recurs with a lot of other ideas, or is there some item that has a particularly large influence on the results, and how to find that out? And some of the things that I'm including that in prior looks at things might have been overlooked is the span of motivations. Why are we doing these things? Trying to come up with a scheme to measure all the disparate approaches on common terms, to include infrastructure development where an interstellar mission requires that. I'm also using the historic patterns of technological advancement and revolution to help with the predictive methods of, because very long time scales we're doing this, and also considering other ancillary advances and the impacts they might have, like the ascension of AI or the energy trends over history. So that's what I'm trying to do. And before I get into the details of how to do that, here's just kind of a look at how the time scale is beyond predictability. Here we have basically a century. And why do I pick a century? Because in the congressional language for the next NASA budget, it didn't survive the final budget, but there was language in there for a suggestion of launching a interstellar mission at the centennial of the Apollo, 2026, and traverse at 10% the speed of light. And if you add up the numbers on that, you're getting your data in about a century. So we're talking about these kind of timescales. And then if you look at Starshot, you know, there's the technology development, their fast transit, but then they have 20 years to also send back the data. What I would like to do is to give you a sense of comparing how much can happen with these sort of timescales. Here's some history lessons. Going from the rocket equation in 1903, which coincidentally was the same year of the Wright brothers' first flight, to the point where we had the first liquid rocket experiments was just 23 years. Another one that I think is a good example, the start of nuclear science to having a nuclear reactor on the power grid was 60 years. So the kind of things that can happen within those time scales, there might very well be some surprises. So the main point of that is that we are talking very long time scales where a lot of things can happen. Energy levels. One thing I want to point out here, that prior chart only covers about this amount of time. This blue line here is based on historic patterns of the growing energy prowess of humanity, the total energy produced on Earth, and the span here is one standard deviation, so there's a huge amount of uncertainty of this, of how much energy does humanity produce and how is that growing over time. The other thing I did is that this is only 1/1,000,000th of what that value is, because we're not going to devote all of humanity's energy to a mission. Why 1/1,000,000th? Well, when I did this study before, that was the comparison between the energy at the time when the space shuttle was going on and the total energy it took to launch space shuttles in terms of propulsion energy. Now we compare that with how much energy does it take to do interstellar missions. For example, the Starshot probes, if you use the value that they're firing for 10 minutes, it comes out to about that power level. This is in joules. And for comparison, the Nagasaki bomb was down at this level. 100 Starshot probes bumps it up to there, 1,000 Starshot probes bumps it up to there. So you see, when we're talking the predicted available energy of humanity, we're pushing it. Some other references, if you imagine a large colony ship leaving the solar system at only escape velocity, where it's mostly not so much to reach a destination, but to have another human habitat extending, being that it's slow, it doesn't require as much energy as a fast, larger probe. But you can see the energy required from that and about when we might have it is a ways off. So two things here. Again, we're talking long time scales of maybe even having the energy to do any of these missions. And also, we're talking energy levels that are multiples of atomic bombs. So we definitely need to be responsible with that. Okay. Another point when choosing what to do, and this is one thing I really want to get across to the audience, we aren't the ones who decide really how much is going to be invested in that. That's kind of a given by other things. You have the Starshot folks that are offering $100 million for seed money, and then the NASA thing, on occasion you get about every now and then a 100K grant or something like that to work on things, about 3 orders of magnitude smaller. Since we don't decide what those levels are, and these are the kind of things that seem to be happening, I want you to think about if you had $150,000 for 1 year, what piece of work would you choose to propose that could actually make progress at whatever level your expertise is? Because I would love it if all the expertise in this room and outside of here could be applied to this, but instead of debating about which mission architecture is better and things that answers are longer term than we can do, if you started next year with something and had the money to do it, what would you actually work on? Another aspect is that when having those choices, which is the best? And obviously best is a matter of, well, who's deciding? In the case of the grant, it's NASA. How much support available, which I mentioned. What options are available, which are the kind of things that people in here are going to come up with. But also, and one that's been kind of overlooked, is why are we doing these things? And I come back to that more. Okay. The plan for the grant is the first year is to really come down to asking the right questions. Not only the right questions of what are the challenges that we need to make, the mission-driven ones, but also what are the prospects that we have to work from. Then the second year, with that outline filled out, is start to make sure that we populate it with accurate information and provide some sort of online database where the experts can upload whatever the performance parameters for their subpart are, and then also have that as a way of sharing that with the public. And that's also when we begin the comparative algorithms. And the third year is the final analysis and recommendations. Also, we're not doing this alone. In the first year, it's mostly working with a NASA advisory group to get feedback. I definitely want feedback from this group too. Community exposure is important. When we get into the second year, then we're going to actually have to pay for some extra help to fill in some of the gaps. We haven't decided exactly how to do that. We know that's going to happen. The one who's creating the algorithms and the process to do this is Jim Gilland of OII. We're actually patterning some of the analysis process over something he did for a Mars comparison. And in the final year, running those algorithms, filling out any further information gaps, and then suggesting, oh, that's right, I have that on another chart, so I'll come back to that. I'll come back to the third year's documentation. As far as the analysis concept, the inputs, the things that we have control over, and this is the main ones that, when sitting NASA down at this tool to see what versions they can come up with, are why do you want to do this and what sort of mission constraints do you want to impose? The other basic inputs are all the predictions of technological prospects. The kind of outputs that we're looking for, mostly it's relational. With these sort of long timescales, it's going to be hard to get absolute answers. So it's like looking at, with other criteria the same, for example, for a given launch year, which mission scenarios seem to require less energy? Even though you can get a value for what that energy is, realizing those are approximations, and it's more for the sake of a relative comparison between these things. And sort of another picture of how that process works. There are the nature-driven challenges. I mean, the physics, the stuff that we can't really change that we have to understand. The distances, energy equations, performance limits of the physics of a device. You have the choice-driven inputs. When do you want to launch? How far do you want to go? Do you want to set the speed or the mission duration? Why are you going? And do you want to have some particular technology pick or technology readiness threshold? All of these sort of things are what we're hoping to set up as variables. And then loaded in there is the data on the estimated performance for not only mission architectures, but mostly the propulsion and power options that go into them. Spreadsheets and plots like this, which are, these are called topological maps. The idea is to try and show correlations between, in this case, mission requirements and the various missions, of which ones seem to have more or less impact. And in this case, the red is the highest impact. So the idea here isn't to select like a single mission, is to try and understand which factors on here influence things more, where we need to put more or less attention. And this is in the levels of, what missions do we do and how do we want to do them, how the technology compares to those requirements, and then how does the technology compare to what we still have to figure out. The third year recommendations, this is where we come back to. Obviously identify what are the knowledge gaps that really have to work on, and recommend a research solicitation strategy. And what I would really like to do is base this after the kind of thing I did with the NASA Breakthrough Propulsion process, which was to have a cycle of research where you look for short-term tasks, something that's 1 to 3 years, to answer just one question at a time. Not how to create a whole vehicle, but some critical question. And let the results of that cycle define what you concentrate on the next one. Also try and span a diverse suite of research approaches. In other words, not all laser sails, not all fusion, but a mixture of things, the healthy mixture of things. And so the grant is to try and figure out a process to make these solicitations and choices wisely. Some interim conclusions so far. The kind of near-term precursor missions that have been talked about, like going to the, just beyond the heliopause and stuff like that, this doesn't really fit with this study. Those are things where you can use traditional mission technology trade studies. And I would very much like to see those missions proceed. And one of the things from those that we still don't have a baseline for is what sort of payload could you send? And how much would that weigh? We don't even know what that is today, let alone the future projections as things go on. And that community can definitely provide that kind of answer. Another one is the idea of passenger ships or world ships is a completely different set of questions. I'm not quite sure how to deal with that yet, so in the meantime we'll be concentrating on just the probes. The other one, to make identical comparisons or fair comparisons, is that for anything that's a given launch year, we'll impose the same payload mass and energy requirements and stuff like that. So any particular version will be delivering the same payload, at least analytically, to see how they compare. Also, they'll be assuming the same infrastructure capacity. In other words, if someone needs a certain amount of space infrastructure built by that time, all of the various concepts will assume the same capacity is available then, which requires us to figure out how to model how these things will change over a century. Just for an example, miniaturization, which is definitely happening, it will, however, reach some minimal level. I mean, okay, how many molecules will it take to take 1 pixel of a picture? How many extra molecules will it take to process that and send it? I mean, there is a finite limit. I'm not sure what those are. These will be approximations, but the thing here is that it's not so much that these become accurate approximations, but that the various methods are compared according to the same timelines. Okay, this is the one of those ones that I was a little bit surprised with in looking into it, that has a larger effect that hasn't really been looked at, the why do we do these things? And there's aspects to that. There's some of the motivations to do it in the first place, where you want to go and how interesting that is, and how ambitious are you going to get for what you do there? Are you going to just fly by very fast, or are you going to go into orbit? And those things make a fair amount of difference on why you want to do it. Now here's the one that's the weirdest. When you think of why are we doing these, it very much changes what sort of work you look on. And when I've looked at a lot of the prior missions and you ask why are they doing this, they'll say, oh, the object is to go to such a destination sometime. And it's like, okay, but why? And for example, if the motivation is survival of humanity, which I kind of think is important, the kind of things you'll end up concentrating on are sustainable habitats, the ideas of world ships and stuff like that. If you're interested in technology development, then what can you do that might actually reach a return on investment? What process can you use to mature the technology? And I think the Starshot is probably a good example where, with not said explicitly, at least implicitly, this is probably motivation. Another one, and I'll say a little bit more about this later, is bragging rights, to be the first to do something. And then there's the basic learn what's out there. Now, with that, for any given mission, you can score how well does it match any of these criteria. And which of these criteria end up on the list and what NASA thinks the particular weighting factors are between them, that's going to be a work in process, and I'm really curious. I just put up my own bias numbers there because I kind of think that was really important. A little bit more on that. Yeah, I already mentioned the survival of humanity takes you into an entirely different scale of importance and line of inquiry, including sustainable life support. Now, the one thing is it also requires sustainably peaceful and meaningful culture on those on board, which is really hard to figure out. But the concept of world ships, separate of the here and now, kind of provides an academically safe, less contentious context to contemplate those problems. I don't know how to do that work. I would love to see that work done, and we actually invited some presentations to deal with some of these issues, so that needs to be in there. The other one, the bragging rights about being first, I'm surprised how often that really seems to be the leading motivation, and when you think about it in the grand scheme of these other things, it's really not that important. It doesn't really serve that much of a goal to the kind of consequences we're doing. And I want us to be explicitly alert to why are we doing these things, because if we understand that, how our priorities might change. Okay, another one about being first, there's something called it goes by many names. I like this name the best because this is what I named it, incessant obsolescence postulate, that no matter when you launch a probe, something more modern is going to get there sooner with more modern equipment. You don't really need to worry about this because this only pertains to if your motivations are to be first. And also a number of things can happen to defer that. And even if your motivation is to be first, there's already equations to exist to show you how to figure out when's the optimum time. So that's not really an issue. Other motivation factors, where you want to go. And I think if you're going as far out where you're reaching intelligent life, that would be a really interesting mission. Or if you're just going to the interstellar medium, perhaps a focal, less interest. But as you go up to these things, they get more and more interesting. And then also, what do you want to do when you get there? Are you just going to measure the fields, fly by very fast, slow down, go into orbit, land, sample, return? I mean, remember, we're talking timescales of a century. So even if some of these might seem premature to think about, to realize that they would carry a whole lot more weight is part of the equation, literally. And these are the more familiar ones, launch-driven chances. What launch year do you pick, and that affects the baselines that things will be compared. How fast do you want to go there? The scale of research support, meaning how fast we'll be able to advance things like this. This really is fairly normal stuff. And the nature-driven challenges. We're talking about astronomical distances, literally, and speed limits. How to survive the journey, not only for the hazards of debris and cosmic radiation, but just the warranty period for the vehicle. How long can we make a space probe last? I remember a conversation with Ralph McNutt, and he said, don't quote me on this, but sorry, Ralph, I will. He said probably 2 centuries at most, but there's not really any work to say how far could we push that? And that would have to be autonomous. Another one that sometimes it's overlooked is there are actual physics limits for some of the ideas we have, that no matter how much you push the technology, you won't be able to get any better. The example I have on here is the specific infills for LOX hydrogen engines. I mean, the theoretical limit is 529 seconds. So if your method is already at 500 seconds, chances are with a lot more investment, you're not really going to improve it that much. And this keys into the pattern of technology advancement, technology readiness levels that we use, infrastructure development prerequisites and things like that we have up. As far as the bottom-up prospects, this one's no big surprise, is what are the options of mission architectures and the various propulsion and power systems. I was asked to include the propulsion physics options in here too. That's like breakthrough space drives that don't need propellant and faster than light. So they're on the table too for being compared. The other challenge is when comparing these things, these are very different methods, so how do you compare them? Well, I already mentioned using launch year as common baselines, but the other one is to distill these things down to the most fundamental currencies of time, energy, mass, power, which you can do that. And then when trying to assess technology readiness, focus on the lowest technology readiness part of the project. Now then there's a category of what I call meta measures, meaning the overall thing of how are you going to compare these. There's the available energy to try and understand how much energy can we devote to that and use historic trends, how much energy you want to devote to a mission. And then here's where it comes down to kind of the central way of comparing it. How much kinetic energy changes are you going to deliver to the payload? Meaning get a certain size payload up to a certain changes of delta V, whether you just fly by orbit or whatever. And then compare that to the total mission energy to make that happen. And the methods you choose change how much extra energy there is. And then do comparisons, okay, which get you the most payload kinetic energy for the least amount of mission energy. To estimate that, no matter whether you're talking sails or rockets or whatever, there are ways of converting those performance levels down to the basics of energy and power and the things that you can do that. The other one that is going to be a little bit trickier to figure out, a lot of these systems have other subsystems such as thermal radiators, and there's certain performance levels for how many kilograms of radiator you're going to need for getting rid of so many watts. And accurate or agreed to baselines for what those sort of values are. So if you have a propulsion engine that has a certain efficiency level, that energy difference has to be radiated heat, which means you have to have such and such mass of radiators to do that. And in some of the prior studies of various architectures, sometimes they go very lenient on some of those numbers, but we want to have them all behave the same baselines. And that gets me to some pricing. This is an unchecked thing, and I was compiling this together and realized I wasn't expecting that to happen, and so I just had to share that. Okay, when looking at energy of some of the propulsion methods, this one's no big surprise that the laser sail basically, and this is all 100% energy conversion, 100 kilogram probe. If you just fly by, it's about, these are the exponent on joules, 10 to the 16th joules, and you can't stop. If you want to do it with a propellantless space drive, which right now has not reached technology readiness level 1, but there are things underway on that, not only would that be roughly the same, but you could stop for twice the energy. That's kind of interesting. Now here's where it gets surprising. The ideas like the wormholes and the warp drives, which require enormous energy levels, which that wasn't such a surprise. When comparing to do rockets for these same things, for flyby or stopping, the energy levels on those are enormous. And this particular example I used, this is the highest specific impulse that I've seen in the literature that's actually been demonstrated in a laboratory. I don't know what that value might be today, but this surprised me that rockets are less energy efficient with things that might be ridiculously power intensive. And just for fun comparison, the rest mass energy of the universe is 10 to the 70th joules, and the amount of energy that might be in a sphere of vacuum energy, depending upon which calculation, could go 10 to the minus 4 joules, which is like nothing, or 10 to the 118th joules. So that's a whole area of physics too, where there's unfinished things, things unknown. And I'm not sure how these will pan out, but I was a little bit surprised by how this came out. Okay, infrastructure. A lot of the missions require infrastructure in order to do them. I'm not going to give them a cost for what it took to create that infrastructure, but if you're building a vehicle, okay, what's the kilograms of materials you'll need to mine? How much energy does it take to mine those materials, process them, deliver them to where you need to build it, and construct and launch your vehicle? For example, the dataless ones need a lot of helium-3. And that has to be mined from the gas giants, and that energy is a part of the picture. Modeling technology advancement. This is one of the more challenging ones because there's so much uncertainty to this. There's more than one thing to model. There's how long it takes to develop a mission when you go from the technology that's already on the table to when you launch a mission. That one's a little less fuzzy. How long does it take to advance a given performance level up through the technology readiness scale so we're ready to use? And how do performance values increase over time? And then there's kind of a mix of 2 and 3 that there are sometimes modest performance gains within a particular technology readiness range. So to try and do that, the proportions between the different stages are going to be set to be some baseline ratio. And granted, these aren't going to be good for absolute comparisons. They'll be sufficient for relative comparisons. And then there's asking, well, for your particular mission, how much mass and energy you're going to need, and then you can kind of pull that out for the mission modeling rates, where it's assumed that a mission that has more energy, requires more energy, is going to take more time. As far as the technology's readiness level Ascent, and there can be different entry points to this, but again, same sort of thing, comparative timelines between those, and then the presumption is that a more powerful device, higher wattage, is probably going to take longer to mature through that scheme. Now, some of these are going to have to be very rough guesses, but again, for relative comparisons, if they're all following the same sort of guidelines, we might get an idea. One that I haven't really figured out how to work in there is some measure of relative difficulty, because there are some ideas that are going to be much harder to bring to fruition than others, and how to throw that into the mix. Now, looking at historical rates, typically, an example of Moore's law and looking at the miniaturization, they do seem to follow an exponential up to a certain point, but the other notice in there is that these things happen in stages, or more specifically, following these S-curves of technology investment. And these curves are repeated time and time and time against history. An example for a prior method is, let's consider the speed of a piston propeller aircraft. Well, it can only go up so fast. If you want to go faster than that, you need to use a different method, like jets, and it too will have its own method. This pattern recurs over and over again, and what's nice about that is there's mathematics to govern this, and by asking what sort of questions, asking the right questions to try and get some sort of model for the various technologies of how they might fare on this. As an example too, there's the point where the technology first becomes obvious that it might actually work. That's this lower point on the curve, in which case you've been working here from the basic physics to get it up to technology readiness level 1 through 3. But then after that, when you have the improvements, it tends not to be one embodiment that gets better and better. You tend to have different versions, and that they're staged at new levels of performance. Say, a new ISP level, which then, once it goes through, it has its own technological readiness level advancements to go up through, and that these things happen in stages. And so as you get higher performance, these stages are longer. And so that's kind of the way that's going to be used to model these relative things. And these are some of the questions to try and get at developing those curves. For a particular idea, what is the upper physics limit? I mean, on some of them. What is the next projected improvement level? In other words, the technology is going on, what kind of performance level are you gunning for, and what is your actual technology readiness level for that? Also, right now, for that given particular approach, the things that are already technology readiness level line, what is its performance value? And then the last one, when that particular method first debuted, what was its performance value then? And those sort of numbers give you enough to where you can model those curves. But does that information exist yet on all the various sort of options? No. Okay, the next steps, I'm going to have a progress review with the NASA Advisory Board on this one-year progress in January. Also, please send me feedback, and this will be discussed. This is something where I'm trying to set up a tool that can help the community figure out what things we do tomorrow for the longer range thing. So if you have any ideas or see a huge flaw in my thing, please bring that up. Okay, now about the Tau Zero Foundation. What it is we're trying to do and some other things like that. And we've toyed around with various mission statements to boil this down into, well, how do you say this? And the grand, large goal is to figure out how to make it so humans can travel to distant exoplanets, which, granted, is very far away. We don't know how to do that now, but that's the ultimate goal. In the meantime, what can they actually do? The mission is break that down into affordable next steps, figuring out what are those next steps and actually chipping away at those. And that covers not only taking things like propulsion energy and energy storage things, technology for near-term type emissions to try and nudge that technology along to even answer near-term commercial needs, which has part of it to do with the funding issue. Also, the research on propulsion physics. And then also trying to educate the community and develop STEM things and other things to help future workforces get into and realize these visions. So those are the kind of things that we're after. It's a longer list too, but these are kind of the key ones. One big change that we've had, about a year and a half, I brought Rhonda Stevenson on board. And for those at TVIW about this coordination, you know that she has been the one I had her do all the dirty work on making sure this collaboration worked out. I discovered when I was running this that even though I was okay with dealing with a lot of technical people on the technical issues, I was not so good on business issues or dealing with non-technical people. Rhonda is way better at that than I am, and she had everything to do with bringing on these other very helpful board members. Jeff Greason, who will be talking later today, his claim to fame, or the one that you might know him about, is the Easy Rocket from X-Corps and the Easy Rocket aircraft that went from that. He's had over a quarter century of aerospace management and engineering positions. He's also a advisor for reusable launch vehicle regulations, heavy stuff like that. Andy Aldrin. He's also had a very long time in various fields, including United Launch Alliance, Boeing, and he now leads the director of the Buzz Aldrin Space Institute, which is a multidisciplinary institute for establishing a permanent human presence on Mars. And Andy is very well in tune with the aerospace community in general and definitely has a lot of very constructive insights. Okay. Rod Pyle. He's a journalist, author, and historian, and he's worked with NASA, JPL, and JSC on publications, has a number of books and even a History Channel documentary. And so obviously when it comes to trying to share progress to the public, that's definitely a needed skill. Bill Towski, again, another long-term executive with a number of business experiences, and he also now helps nonprofits to do a better job, and so there. And then if there's anyone in here who doesn't know Paul Gilster predates Tau Zero by a few years with his book Centauri Dreams and the regular news forum that he has. He has been very valuable from the beginning on helping shape Tau Zero. Okay, some of the things we do. When it comes to spreading the news, I just mentioned Centauri Dreams. And if any of you don't know about it already, please check it in. Two cool things about it. He limits what he writes about to what's in the peer-reviewed journals, and he has citations, and he distills that down into something for a more general audience. And then there is a moderated discussion forum for that, meaning that you can comment, and the crazy people and the unpleasant people are filtered out. So the fidelity of those discussions is quite good and quite as meaningful as the article itself. Something new, this just happened within the last few days. There's a PBS program called Janet's Planet. We're going to start collaborating with her about educational opportunities in STEM and things like that, about how to reach future educational workforces. And one thing I want to say about the STEM stuff too is that, and a fair criticism that I've heard is like, well, should we really be encouraging kids to pursue these things if there aren't going to be jobs? And so I realized, well, you know, one of the things we're going to have to include in that is what sort of advice to get into employment and to start making contributions. And so that's probably some of the stuff we're going to have to cover too. Obviously, there's our website and other social media stuff, which Rhonda has been taking most of the lead on. And I recently started giving a short course on Interstellar with the main concentration on about 2/3 of the propulsion physics. I gave that at Technical University of Dresden last year. I'm scheduled to give it at Purdue. It's a 10-hour course. Oh yeah, when I was at Dresden, we also had the opportunity, Pete Worden came out to give a talk about Starshot while we were out there and to find out the other things that were going on at Dresden, which I'll say something about. So that was a really cool experience. The NASA grant, already told you about that, you know what that's about. And the propulsion physics research. We hope to get into technology things in the future, but right now we've already been working on that. We had our anchor publication in 2009, a book to compare the ambitions of faster-than-light travel and non-rocket space tribes to where is the physics today and what would be the next research questions you'd want to answer. I'm going to say a little bit more about Dr. Martin Tymar's new project at the Technical University of Dresden. We also have George Hathaway is one of the speakers later, and Eric Davis trying to do experiments on demonstrating negative energy states, which has relevance to faster-than-light questions. These are very preliminary physics things, but they are things that are now attackable problems. Okay, the Technical University in Dresden, Germany, Dr. Martin Tymar leads this. Some of you might know him from his electric propulsion days. Well, he decided he wanted to do propulsion physics stuff when he grew up, and he actually started a project to do it. He's been doing it since 2012, and now he has a funded program that started this year and runs for 4 years. These are some of the examples of experiments that have been conducted. These have already been conducted and published and shown ideas not to work. He's testing the EM drive, he's testing the Mach effect thruster. He also has some other experiments to test some other related unfinished physics issues and stuff like that. It also includes some theoretical work. These are some recent publications from Tymar and his other people, including developing a scaling model for the Mach effect thruster, and other things about trying to understand how gravity and electromagnetism and space-time are included. And other topics for which the publications are not happening yet are what is an inertial frame and can we use that for propulsion? And I would love to talk about that at length about that. That's something I can definitely go into, which is subject in itself. Also, negative mass propulsion. The idea goes back to, I think, 1956. But of recently, there's been a variety of experiments indicating, what do they call it? Virtual or effective negative mass effects, to start looking at those and see, okay, is there really something here that we can work with? As far as future interests, we're hoping to get into more technology research stuff, energy generation and storage, whatever next step kind of propulsion things we can do. I mentioned the STEAM and the STEM. This was before knowing about the Janet Planet thing. We're also hoping to get some university affiliations squared away. Right now, there's the one with Dresden. And here's the other part that has relevance to the community. A few years ago when I started this, I had a fairly robust network of subject matter experts. Over the years, that's kind of fallen apart. And so now the time has come to start rebuilding that network of subject matter experts and to figure out how to do that in a sensible, effective manner. So that's something that's coming for the future. Okay, I want to say something about today's presentation because there was a reason why we picked and asked for the kind of things we did. There's sort of a sequence here. The first talk is about building infrastructure, which is relevant to getting to the point where we can do some of these more advantageous interstellar missions. Then there's a talk about a propulsion method, but the point has to do with considering that deceleration is really something we'd love to do. Next comes to energy. I mean, these things are going to need energy, and energy on the vehicle is, and one of the candidates is antimatter. So as an example, how can you store antimatter more densely? And there's work going on in that. And then, how can you produce more antimatter? And then the next line, if you notice, this is kind of going from near term to far term. The talk I have by George Hathaway, George has done a lot of experiments testing some outrageous claims. And how many of you have seen the news stories about the EM drive? Okay. I found that extremely painful because the threshold of quality on the research is not enough to give you definitive results. So I invited Hathaway to give a talk about, if you want to consider those sort of things, what are some of the performance thresholds you need to reach in order to give defensible results? And I thought that was something that was worthwhile. Okay, as far as the afternoon sessions, there has been some changes, but the things I wanted to point out, remember in the beginning I mentioned that there are sociological issues that are really important here that I don't know how to cover, that should be covered, and so I invited some presentations to at least beginning to talk about that. This one is talking about how do we handle, examples of handling lethal energy levels responsibly. Then there's one about how do you have a sustainably peaceful society on a world ship? These are things that they're really important. I don't know how to solve them, but I wanted at least to have some way of getting the dialogue started on this. And my closing slide before I open it up to questions. I like the idea of step by step, the ladder to the stars, and I have to actually do the plug. A decade earlier, we came up with the slogan ad astra incrementus, which means to the stars in ever increasing steps. I like that word about incrementus, it has dual meanings. But then we were scooped many years, centuries before that by Confucius. A slight translation, Confucius was a journey of 1,000 miles begins with a single step. Well, 1,000 miles in the language of the Chinese things is really 50 kilometers, and so if you up that to our kind of things, a journey of 5.3 light years begins with a single step, and so that's 10 to the 11th orders of magnitude higher, but that the philosophy has been there all along. To do these really ambitious things, we need to figure out what are the next small steps that we can take today smartly and start making them. And with that, I will open it up to questions, which I understand we have 5 minutes left.
Okay, I'm Bill Gardner, an Analtech Mars Society, National Space Society, among a few other things. Now TVIW, I would like to add. Marc, so as part of your breakthrough physics and propulsion project, I think you conducted with Les back in the early 2000 period, you stated a couple conditions for achieving interstellar flight. And would you comment on where you stand with those particular conditions, and have you withdrawn, modified, or updated those conditions?
Which conditions do you mean? Like the ones for the study, or the ones that...
The basic conditions for breakthrough physics propulsion. Remember you gave two conditions, FTL?
Oh, mass, energy, speed. Oh, they're identically the same. And as a matter of fact, all the, even though we found errors in the book that need correcting, there's also been advances since we published the book. But in philosophy, in principle, the stuff that's in the Frontiers of Propulsion Science book of trying to compare these ambitions to unfinished items in physics, that still stands, a lot of those, and a lot of those questions have not been pursued. Some have been pursued and there's been some progress. But that idea of attacking the topic in that manner, of what are those next step questions to try and chip away at, and that's still the same. I also want to say that with like the NASA study on this, I'm in the convenient position that I do not have a favorite mission. I mean, I'm more well-versed in the propulsion physics stuff, but that doesn't mean I think it's the greatest thing. I think it's a curious thing to study, but I don't know how the results are going to turn out, and I'm delighted that I don't have a conflict of interest or bias on that. So I hope that means that the fidelity of those results will be good.
Thank you.
Next question, please.
Morning, Mark. Nice presentation. I'm Greg Matloff, and I've been around the interstellar community for more decades than I care to admit.
Longer than you've known better.
Longer than I've known better. Okay, in the 1970s, there was a lot of discussion that began about bootstrapping to the stars. And people
the 1970s about what to the stars?
Bootstrapping. People like
bootstrapping. Okay.
Heppenheimer and Drexler, later me, and Jeff Landis have done work on, let's say, you build a space hotel, it evolves into a space habitat, they build more space habitats. Ultimately, as Jeff Landis has said, there's a percolation effect, and one of them decides to fly off to Alpha Centauri. Could you, in your approach, which is a very nice approach, and a necessary bureaucratic approach, put in something for bootstrapping? Is it possible to quantify this?
Okay. Well, the way I've been tackling that so far is to try and predict how the infrastructure is going to grow over time, assuming that it will, just for the near-term space things, which is also why the next presentation deals with cislunar infrastructure creation, and to try and estimate how that will change over time, and also estimate, well, if you're going to use that, how much do you need, in some way of quantifying that comparison. Now, as far as those evolving into steps on themselves, it's kind of becomes implicit when you look at the patterns that I'm using for what are trends of growth and the S-curve patterns and the exponential or whatever, they fit so many things, including things that get bootstrapped. So I'm hoping that that sort of analytical tools will at least model in principle, if not explicitly, that sort of philosophy.
Okay. Thank
but
you. Yeah.
The other way to try and tackle it is that if over the years when we are asking for more substantive details to fill in things, if someone had a specific mission architecture that included those steps lined out to help flag out what might be precursors for each, that would probably be a cool thing to look at.
Okay, thank you.
One more question.
Doug Loss. Has any consideration been given to levels of societal interest and awareness in interstellar efforts, and how would that factor into your models?
Okay. When it comes to the NASA grant part, there is not an element to try and figure out how to make this more interesting for the public. But if you notice, when it came down to what makes a mission more interesting, and what might make it more valuable, and to be explicit about that. I mean, if a mission and some of the work has to do with improving the chances that humanity will continue to survive and even thrive, that would probably garner a lot of interest. But to be aware of those factors, but there's no other advocacy on that. When it comes to the point of Tau Zero, we are trying to do that, but we're trying to do it more from the point of conveying the information of what's out there as accurately and impartially as we can, and then now our new things to try and get into STEM and outreach and mentoring programs and things like that. Okay, I understand I have to stop. So that is, getting the people excited is a hard thing, and kind of peripherally trying to do that. Okay, thank you.